Hello everyone, welcome to another lesson on circular motion. This one is lesson 3 and we're getting into vertical circles. So to begin with, we are going to think about two situations, one where the object is at the bottom of the swing and one where the object is at the top of the swing. Now we're going to use an object that is attached to a string or a cable so that there is a tension force. So let's go ahead and imagine we have an object on a string and it's at the bottom of a circular motion situation. So here's our circle. Let's have the string attached to an object at the bottom here. Obviously the object's going to have a mass and let's say it's traveling in this direction. So clearly we've got a radius and we can start radius of the circle, we've got some speed, we've got some periods, all of those good things to think about when we're talking about our equations. We have these guys that we are familiar with, and we should be getting quite used to those. So let's think about the forces. As always, we're assuming that the ground is here, so this is the Earth. So this is down towards the Earth, and then let's just draw a sun. This would be up towards the sun. So we're sort of positioned on planet Earth, as we can imagine quite easily. So clearly we're going to have a force directed down towards the Earth, and we call that the force of gravity. But we'll also have a force directed up because, of course, this motion, this circular motion, has to result in an acceleration to the center. So wherever the object is, there will be this, wherever the object is in the circle, there'll be this acceleration to the middle. That's the centripetal acceleration. So there has to be a force that comes with that, and that force needs to actually be bigger. So my red arrow here for the force of tension needs to actually be bigger than the force of gravity, because otherwise if the force of gravity arrow was bigger, then this arrow would win and the object would start to take a trajectory down, given that its trajectory from the circle would tend towards tangential. So if the force of gravity was bigger, then you can see that this would start to make a trajectory down. But what it actually happens, because it's in circular motion, it continues on this loop up. So at this instant in time, it has to accelerate up, which means we need the force. Okay, there we go. Now let's do our analysis. And of course, we always want to be good physics students, and we're going to be using our F-net expressions. So we'll say that the net force acting on this, by the way, we'll just communicate that we're doing this in the y direction, the up and down. We're going to ignore the x for now. So in this direction, in the y direction, we are going to say that there are a sum of all these different forces, okay, however many there are. Now, what we know from our previous explanation on centripetal forces is that the net force, the sum of all forces, is the centripetal force if it's going in a circle. So this is a major concept, this idea that we can take the net forces and turn it into a centripetal force. That's really key. Now we just have to decide, well, what is our positive and negative? And so here's a little rule of thumb. To make our lives easier, we're going to want the net to be positive, and therefore the rule of thumb is that we're going to treat the center of the circle to be positive and the outside of the circle to be negative. So now you can see that you've got this, the sum of all forces is going to be the positive tension force minus the gravitational force. Now this makes sense if we solve now for the force of tension. So you would assume that at the bottom of the string, it's going to be a maximum tension. Okay, so let's just prove that to ourselves with algebra. So here we go. The tensional force, if we rearrange and solve for Ft, well, that's the force coming from the centripetal acceleration plus this Fg. Okay, so that is that's adding these two forces together, that's going to give us a maximum force, which makes sense. At the bottom of the circle, that's when you're in the maximum force. So now we'll do the minimum tension situation, in other words, the top of the swing. So exactly the same situation. This time the object of interest is spinning around and it's reached the top of the circle. So once again, we'll go ahead and put in that we have a gravitational force coming downwards. And this time, because there is, it's still in circular motion, there's still tension in this string. There's still a tension, and that tension, of course, is pulling it in towards the center. So we have two forces now acting towards the center of the circle. So we're going to treat the center of the circle to be positive, the outside of the circle to be negative, and now we just go ahead and we do exactly the same analysis, again recognizing we're doing it in the y. So we're doing our F net expression, which is the sum of all the forces, and we know that if we do that properly, it's the F net is the FC, the force centripetal. So here we can add these together. We're going to say that the Ft plus this Fg is equal to the force centripetal. And now we can algebraically show that it's going to give us a minimum tension. If we use our algebra, we'll show that there's a minimum tension here, solving for Ft. So let's do that in green. Ft is now going to be equal to, well, that's obvious, Fc minus Fg. So this is the minimum force acting through the tension cable. It's the centripetal force minus that Fg. So a quick example. 2.8 kilogram object attached to a massless rod spun in a vertical circle. Given the period, we need to know the minimum tension. We're given the minimum tension to be 20. We need to know L, the length. So we've got period, we've got mass, and we're told minimum tension. This minimum tension is actually telling us information. So this is saying that it must be at the top of a vertical loop. Okay, so let's draw that out. Let's put our circle in. Go here. And we can start putting in the object. Let's make it a square this time. So there it is. It's on a massless rod. It's at the top. It's got some sort of speed. Now, we know the force of tension. We're told that the minimum force of the tension is 20 newtons. So let's go ahead and just quickly analyze using our free body diagrams. We'll be good physics students. There's a tension there. Of course, there's also gravity, and we know that when we do our analysis in the y direction, the F net is going to be equal to all of these forces, and that F net becomes the Fc. And so the Fc, the force centripetal, is a product, is the sum of the two. We're adding the two things together: force tension plus force of gravity. And since we're given period, we're going to be going ahead and using the equation for centripetal force that has the period in it. So 4 pi squared Rm over T squared is equal to the force of tension. Well, I'm going to put that in as 20 newtons because we're told that value, plus Fg, well, that's mg. Now, we need to solve for the length of the rod. Well, that length of the rod is going to be the radius, right? It's this length of the rod here. So I'm trying to solve for the radius. So let's expand that out and put some values in. So there we go. Once we get all the numbers in there, I'm just being a little bit overly cautious with brackets, making sure that we do our bed mass rules correctly. But you can see that you've got the force tension plus mg, then this value multiplied by the period squared. That should actually be squared. There we go. And then divided by the mass, 4 pi squared. And that gives you 22 centimeters is the radius. Okay, so now we have apparent weight. This is the feeling that you get from interacting with a surface. Normally, of course, we interact with the gravity and the surface of the Earth, and our apparent weight is just 1g, in other words, mass times gravity. But when we're traveling and we experience hills and bumps, though you can think of those hills and bumps as being part of a circle. So let's think about the top and the bottom of a circle, and we should get a sense of what that kind of looks like. So first of all, bottom of the hill, let's think about that. So here's a circle, and we can imagine that this might represent, if this was the road surface and then it came down like this and up like that, at any given point you could potentially have a vehicle, here's my car with its wheels, at the bottom of this circle, essentially. This is the bottom of a hill. Okay, so let's quickly think about the forces. Again, we're doing exactly the same thing. I'm just going to go ahead and say that, of course, this is Earth down here, and I know it's obvious, but we'll do it anyway. The sun is up here, so we've got up and down as normal. We'll call this the force of gravity. Now, hopefully you can intuit that at the bottom of the hill, you're going to experience, or your apparent weight will feel heavy. Okay, so this is the point in the motion where you are going to feel the heaviest. And so this Fn, this Fn value is going to be bigger than the Fg. Okay, that's going to give you that experience of feeling heavier. Now, remember, we are going to say that the inside of the circle is positive and the outside is negative, and that's important so that we can then do our Fnet expression. So we're going to go Fnet is the sum of all forces, and in this case, the sum of all forces, as we've said before, is the centripetal force. So we're saying that the centripetal force here is going to be the Fn minus the Fg. Okay, and that's the condition there. Of course, proving now that our intuition is correct, we solve for the Fn. So in this case, the Fn is going to be Fc plus Fg. So that's going to give us a big value. We're adding these two together. It's going to give us a big value for our apparent weight, which makes us feel heavy. For the top of the hill, we do the same thing. We're imagining that we're driving along, and the road goes like this. Okay, so obviously we can think about this hill in the road actually having a radius, just like we had before, to the middle. This time the car is on the top of the hill, up here. And at this point, once again, we treat the middle of the hill to be positive, the middle of the circle to be positive, and the outside of the circle to be negative. I'm going to go ahead and put my Fg in right away, because there it is. And the car is going at such a speed that it doesn't take off. It just makes you feel lighter. You can think about those feelings when you go over a big bump. You kind of get that lurchy feeling where your stomach goes into your chest. And that's because the Fn is being decreased. Obviously, the faster you go, the smaller this Fn becomes, eventually becoming 0, which would be you taking off and jumping. That's not what's happening. We are still in circular motion. The wheels of the car do not leave the hill. So there is still an Fn, but once again, when we do the Fnet analysis here, we know that the Fnet is the sum of all forces, and that's going to be the centripetal force, positive down to the middle of the circle, so that's going to be Fg being a positive, and now we subtract the force normal. This means that when we solve for the force normal, we are going to go Fg minus Fc. This, of course, proving to ourselves that indeed the top of the hill is when you're going to feel the lightest, because we've just proved it. We're subtracting a value away from Fg. It's going to be less than the bottom of the hill. So, quick example. Obviously, here's our hill. It's the bottom of the hill, and we've got this radius of curvature given. Now, in this case, we have a car and and a person that's given as our mass. So we've got to be a little bit careful here. I'm going to draw these out. But rather than drawing the whole car, I'm just going to draw the person sitting on the seat of the car. In fact, I'm going to use blue to show the car. So this seat of the car represents the car. And so we can think about these as being two separate objects. Now, the force normal that you're experiencing is, of course, coming from the interaction of your butt with the seat. So actually, what we're interested in here is the thing that's doing the circle that we're interested in is the person, the object of concern, which is the 84 kilogram person. And it's the object that is being pushed to the middle. So that Fn is coming from that interaction with the car. But notice that we only are interested in this 84 kilogram object. The 1200 kilogram object, that is just doing the pushing. So it's not actually part of our analysis when we're doing our forces. So that's a really important way to think about things. In this case, the 1200 is a bit of a distractor. It's meant to make you think about it. Either way, of course, we're going to have an Fg here as well. And so when we do our proper nice physics analysis, we're going to say that the sum of all forces is going to be equal to Fc, because we've got used to that concept now. So now we can do the sum of all forces. We're going to treat, of course, the middle of the circle to be positive, the outside of the circle to be negative. So we're going to say that means that our Fc is positive. That's good, because our Fc is always pointing to the middle of the circle. And the Fn is the positive, and the Fg is the negative. Just as a side, and while I remember, I want to make sure that I don't fall for this trick as well. Of course, 91 kilometers per hour is not the units that I want to use. I want to be in meters per second since I'm using forces. So I'm going to get rid of my hour by putting on the numerator, giving myself seconds, and then I'm going to get rid of the kilometer by putting it on the denominator and give myself meters. And of course, there are 1,000 meters in a kilometer, and there are 3,600 seconds in an hour. So I cancel out my hour, I cancel out my kilometers, and I get 25.2777 meters per second. So that's actually my speed. Okay, now we can expand out our condition, our physics over here, and we can add in these values using the mass of the thing doing the circling that we're interested in, because we need the maximum scale reading. That would be the scale that you're sitting on, I guess, between your butt and the seat. Well, I'm given V, so let's go ahead and put that in. Well, actually, first of all, I'm solving for the force normal. That's going to give me my scale reading. That's the thing I'm looking for. So the force normal is Fc plus Fg. Now that makes me happy, because I know that at the bottom of the ramp, I'm going to experience the heaviest apparent weight. So adding these forces together makes me feel comfortable that I've got a larger force. So let's solve for Fn. Now I've got velocity, so I'm going to use v squared m of the person over this radius plus the mass of the person times gravity. And if you plug those numbers in, you're going to get 4,000 or 4.40, because we're in three significant figures here, times 10 to the 3 newtons.